Welcome. In this session on natural deduction, we'll explore the concept of completeness. Completeness is a metalogical statement. That is, it's a statement about a logical system. As with consistency and correctness, completeness is saying something very important. In the case of natural deduction, it is complete, which means that every semantic entailment that holds can be proved. Let's state that in some metalogical statement. What we're saying is, suppose that the set gamma is a set of premises. So it's premise 1, premise 2, and so on until we get to premise n. And completeness is the statement that if the premises semantically entail a conclusion, then from the premises you can use the rules of natural deduction to arrive at the conclusion. The way that we usually handle a semantic entailment is we write down a truth table. An important part of natural deduction is that a truth table is outside the logic. It's about the logic. So if you write down a truth table, that can be a counterexample or it can be an inspiration, but it's certainly not a proof. Let's take a simple example that we've already looked at. So let's consider something that we thought might be a theorem, and that is, let's consider the formula, which is P implies Q or Q implies P. And if we look at this, we might say, well, it's unclear whether or not this disjunction is always true. And in a previous session, we wrote down the truth table for it. And the truth table was, here we have our two atoms, P and Q, and the four combinations of truth values that these can take on are straightforward. And what we found was that our formula, P implies Q or Q implies P, well, we can look at this and we can fairly immediately get our result. P implies Q, well, that is true when they're both true, so that must evaluate to true. P implies Q is false, but here Q implies P, the right disjunct, is true. And here, a false antecedent implies anything, and so this must always be true. And as I just said, this is not a demonstration of the truth or that this is valid in any way. It is, however, an inspiration. So using that inspiration, we might say, well, regardless of the value of P and Q, this formula is always evaluating to true. So what we might try is we might propose a sequent, which is, from no premises at all, we might suppose that P implies Q or Q implies P, and now we're back in the world of proofs for natural deduction. We have no premises, and so the only thing we can begin with in our proof is our conclusion, and we would write down our conclusion as P implies Q or Q implies P. And looking at this, it's not immediately clear how to begin. I'll give you a little bit of an inspiration. I'll say, consider the law of excluded middle. The law of excluded middle plus disjunction elimination can often get us out of some difficult spots. What could we suppose? Well, we could suppose the left disjunct. We could suppose the right disjunct. Instead, let's look at the law of excluded middle applied to one of the atoms. Let us suppose, I will arbitrarily pick, let's suppose we propose P or not P as our first statement, and that would be from the law of excluded middle. Using forward reasoning, we could say, oh, I will use disjunction elimination. And the way that we use disjunction elimination is that we write down the two boxes, and after we've written down the two boxes, we state the reason that we use to arrive at this, and that would be disjunction elimination. We then put the left disjunct into the top line of the first box, so that would be P, and we write down our reason is that's an assumption. And we then copy our goal, which in this case is the conclusion, into the bottom of the box. So that would be P implies Q, or Q implies P. Likewise, we take the left disjunct and put that as the top line of the second disjunction box. So that would be not P, and that would be an assumption. We would copy our goal into the bottom, which is P implies Q, or Q implies P. And what I would then do is I would then examine, taking the first box, I would examine this including all of the lines that precede it that are within scope, and ask myself if I could use any forward reasoning. And the answer is nothing comes to mind. Instead, I'll look at the goal of this box. And the goal of this box is a disjunction. And one way that I could arrive at that disjunction is by disjunction introduction. If I try to introduce the left disjunct, that doesn't look very good. If I try to introduce the right disjunct, oh, this is an implication. And so I think that you can probably fill out that disjunction box. And so I could arrive at this. So I'll note that I'll arrive at that by disjunction introduction, and I'm aiming at that, so that would be type 2. Let's take a hint at this. Here I take the top line of the box, and I look at everything that's within scope, and everything inside this box is not within scope, and the only thing I have is my law of excluded middle. That doesn't seem very profitable, very useful. So I then say, what could I do with my goal? If I look at the goal, if I try to show that something implies a false assumption, that might be difficult. If I try to show that from a false statement I can arrive at an implication, that is something that we've already looked at in previous sessions. And I will note that we could arrive at that using disjunction introduction type 1. The rest of this may be a useful exercise for you to try. And so what we're doing here is we're observing that because of completeness, when we've written down the truth table for a sequent, in this case it was simply a conclusion formula, but when we've written this down and we've established that there's a semantic entailment, that's a hint to us that there exists a proof in natural deduction for that sequent.